Hi, Year 12. I hope you're all well. Right, as I've said in my email, I've got a super busy Friday going on, so I'm not going to be able to do a live sort of interactive lesson on Teams, but I did still want to provide you with a bit more support than just saying, get on with these questions. So what I've done is I've recorded this video to go through past paper questions 5, 7, and 8 from your Alcohols question pack. So the first thing I would like you to do is have a go at completing those 3 questions first. So spend half an hour, 45 minutes, however long it takes, reviewing those 3 questions. Give them a good go yourself, and then watch the rest of this video so you can mark your work. You'll get a bit more of my explanation to go along with it to explain, you know, what the answers are, why they're the correct answer, all that sort of thing. Okay, right. I'm going to assume at this point that you've already paused the video and that you've had a go at those questions. So I'm going to start reviewing them now. So question 5 starts off with this sort of reaction sequence, all these different ways of producing ethanol. So we can start off with glucose with reaction 1. We can start off with bromoethane with reaction 2. We can start off with ethene reaction 3. So part A says reaction 1 produces a 15% solution of ethanol. It is claimed that the ethanol produced in this way is a carbon neutral biofuel. Write an equation for reaction 1 and name the process. Write an equation for the complete combustion of ethanol. Explain why the ethanol produced by this process may not be a carbon neutral biofuel. Right, it's really important that when you have a wordy question like this, as you go through your answer, you tick off that you've done all the bits that the question has asked. It's a 5-mark question, which you'll see down here. So it's really important that you actually get 5 marks worth of information down on the page. I don't mind people losing marks for getting things wrong. I don't like it when people lose marks because they answered the first 2 bits of the question, but they just forgot the 3rd bit. So you need to make sure you've got a system. So reaction 1, we're starting off at glucose and we're going to ethanol. So we've got to write an equation for reaction 1 and name the process. So the process is fermentation. That's just subject knowledge, you just need to know it. Write an equation for it. So we're starting off with glucose, C6H12O6. During that fermentation process, we don't need to add anything to it. Okay, so don't add anything else on that left-hand side. It's going to make 2 lots of ethanol, so CH3CH2OH, and to get it to balance, 2 lots of carbon dioxide are released. So this sort of is subject knowledge. It's maybe equation to know, but to be honest, as long as you remember you start with glucose and end up with ethanol, I think figuring out what the byproduct is and balancing it is doable as well. Okay, so we've done the things that that first bit of the question is asking us. Write an equation for the complete combustion of ethanol. So complete combustion, CH3CH2OH. If it's a combustion reaction, we need to add oxygen. And because it's complete combustion, we are going to form carbon dioxide and water. And then we need to balance. So 2 carbons means 2 CO2. 6 hydrogens means 3 lots of H2O. And then if we add up all the oxygens, I've got 4 oxygens there. I've got another 3 oxygens there. So there's 7 oxygens in total on this side. I need to have 7 on this side. I've already got 1, so I need to put a 3 in front of the O2 to make it balance for oxygens. So I've now done that second part. Okay, final bit. So 2 marks worth of a question left to get. Explain why the ethanol produced by this process may not be a carbon neutral biofuel. Okay, so 1 mark of this is for explaining what are the reasons which causes CO2 to be released into the atmosphere. So even though our plant takes in carbon dioxide to produce glucose, and then when we burn the alcohol that we've made, it releases the same amount of CO2, what other process is there that could actually release CO2? So we could say harvesting the crop. We could say transportation. We could say distilling. And then the second mark, it's for saying can also release CO2 into the atmosphere. Now, to get this mark, to get mark number 4, you can't just say other processes release CO2. You've got to name a specific bit of the, the production of the ethanol, which could release additional CO2. So harvesting the crops could, transportation could release CO2, the distilling process could. Any of those 3 would be fine. Okay, right, next bit. So this is the process that occurs in reaction 2. It says name and outline a mechanism for reaction 2. Suggest one reason other than safety why this method is not used in industry to make ethanol. Right, so name and outline the mechanism. Let's do the mechanism first. We're starting off with bromoethane. Now, if we're ending up with an OH group on our molecule, we need to have an OH nucleophile. We don't need to state that it comes from sodium hydroxide, but that is the case in this situation. So 1 mark for the curly arrow pointing to the carbon, 2nd mark for the curly arrow breaking off the bromine. And then that leads us to our product. And the bromine will be floating off on its own as a bromide ion. Okay, so of that, we get 2 marks for our curly arrow. So there's mark 1 and 2. The mechanism is nucleophilic substitution. Okay, so that's going to get us a mark. Oh, it does actually say, apologies, I need to read the question properly. Give a reagent and condition. So our reagent is going to be NaOH or KOH. Either of those will get you mark number 4. And our condition is that we need to have aqueous. Conditions need to be dissolved in water. So that is mark number 5. And then finally, suggest one reason other than safety why this method is not used in industry to make ethanol. Okay, and there's a number of options for this. So you can have any of the following. Okay, you get a low yield. Okay, you can also say that it's a slow reaction. You could also say that, and this is the one that I would pick, bromoethane is expensive. Okay, bromoethane is actually really useful to make loads of different things. And we can make ethanol from relatively cheap things like glucose. So why use a really expensive starting material to make ethanol when you can make ethanol from a much cheaper one? So any one of those will get you the mark for explaining why we don't tend to use this method to make ethanol. Okay, and then the final bit of this question, and it says, for reaction 3, we're given the sequence here, so going from ethene to ethanol. It says, identify a suitable catalyst for reaction 3, identify the type of reaction, give 2 conditions in addition to the presence of a catalyst, necessary reaction 3 to produce a high yield. Okay, so identify a suitable catalyst is going to be concentrated phosphoric acid catalyst. You do need to say concentrated for that. You can't just say phosphoric acid, okay? The type of reaction, so we've done that bit. Type of reaction, we can either call it hydration, or you can call it electrophilic addition. Hydration is what I would go for because you're adding water to something, but electrophilic addition is also a viable option. Right, we've got then to have 2 further conditions for this reaction, but not to do with a catalyst. So any 2 of the following would be fine for this. So firstly, excess ethene. It says specifically we want to get a high yield. So one way of getting a high yield in any reaction is to have an excess of the reagent to ensure that there's plenty of it around to react with. We could also have the excess of our other reagent, which is steam. That would also be fine, okay? We could say remove the ethanol as it's formed. This is actually, even though this doesn't necessarily show it, this is actually a reversible reaction. And one way to reduce the chance of a reversible reaction going back in the other direction is to remove the product as it's formed, okay? Remove ethanol as formed. Final options, I suppose you could say. We want a pressure, and these are the ones that you may want to put as your answer because these are the kind of the clear-cut things which are in your notepad. A pressure are between 50 and 100 atmospheres, and then a temperature of 450 degrees C, okay? So 5 to pick from there. So we've got Mark 1, Mark 2, and then Mark 3 and Mark 4 are for any of those remaining bullet points. Okay, right, so we're going to move on to exam question number 7 now. So let me just find that on the notepad. So here, propanoic acid can be made from propan-1-ol by oxidation using acidified potassium dichromate. Propanal is formed as an intermediate during this oxidation. So if we just remind ourselves, you can go from a primary alcohol, you can go then to an aldehyde and go all the way to a carboxylic acid. So this is saying we're trying to get from the alcohol to the carboxylic acid all in one go. We don't want to stop off at the aldehyde. So state the color of the chromium species after the potassium dichromate has reacted. Well, we should know that the color change for potassium dichromate as we oxidize any of these species, it goes from orange to green. So state the color after the potassium dichromate has reacted, our answer is green. Describe the experimental conditions and the practical method used to ensure that the acid obtained is a high yield. Draw a diagram of the assembled apparatus you would use. Okay, so for this one, firstly, we got to decide, are we dealing with reflux or distillation? Okay, so describe the experimental conditions and the practical method used. Draw the diagram. So the conditions, we're going to be using reflux for this because we don't want to stop off at the aldehyde. We want to go all the way to the carboxylic acid. Our apparatus, oh, I've just realized I've missed a bit, sorry. The other condition is if we want to go from our primary alcohol all the way to the carboxylic acid, we need to have lots of the oxidizing agent. We need to have an excess of the oxidizing agent. If we've only got one lot of oxidizing agent, we'll only get as far as the aldehyde. So reflux gets you a mark, but also excess potassium dichromate will get you a mark as well. Okay, right, our diagram then. Now, I did mention in our one of our lessons previously about how to draw the diagram for reflux distillation. So remember, mark number 1 is that your condenser needs to be connected vertically. So there's our vertical condenser. And remember, your condenser cannot look like this. I know it kind of looks the same, but it's just not. So let's not cut any corners with that sort of thing. And then the second mark is for apparatus that works. I would probably add a few more little details in here. So there's our reaction mixture. We're going to have water flowing in. We're going to have water flowing out. There's a preference to which way they'd flow in and out, but for the purpose of this diagram, I wouldn't worry about which one you use for which. And then remember, the second mark is for apparatus that works. So you got to make sure there's no little gaps. Make sure that this is open. Okay, it can't be sealed because the pressure would build up as we were heating up our mixture. Okay, so that's going to get us our 2 marks for the diagram. Describe the different experimental conditions necessary to produce propanal in high yield rather than propanoic acid. So for this, we need to use distillation. So that's going to get you a mark. And because this is a 2-mark question, we need to go into a bit more detail. And that means by using distillation, it removes the propanal to prevent it oxidizing further. Okay. So by having distillation, by having our condenser connected horizontally, it means that as soon as the propanol is formed, it actually gets removed from the reaction mixture anyway, so we don't risk it being oxidized a second time. Right, propan-1-ol is a volatile flammable liquid. Give one safety precaution that should be used during the reaction to minimize this hazard. Right, this is something which you'll pick up when we do this practical in school. Remember, it's one of the required practicals you have to do. Normally for distillation or reflux, if we were to demonstrate it with something in school, you might heat this with a Bunsen burner. But actually, because we're dealing with organic molecules here, alcohols and aldehydes and carboxylic acids can be very flammable. So you want to heat it up, but using something which doesn't involve a naked flame. Okay, we call it a heating mantle, which is like an electric heater. So our safety precaution is avoid contact with flames. Okay, Part C, a student followed the progress of the reaction of propan-1-ol to propanoic acid by extracting the organic compounds from one sample of the reaction mixture. Give a chemical reagent that could be used that would enable the student to confirm the presence of propanol in the extracted compound. State what you would observe when propanol reacts with the reagent. Right, so here, what the question is saying is, let's go back to my diagram. It's saying we've got our alcohol in here. We're trying to oxidize it all the way to the carboxylic acid. So we're heating it up under reflux. We've got our potassium dichromate in here. The question is, how do we know that the reaction is finished? How do we know that it's actually turned all of the alcohol into the carboxylic acid? If we want to make sure that it's done that, we need to check that there is no aldehyde in there. Because if there's any aldehyde, it means the reaction's not finished yet. Some of it still needs to oxidize. So we need to test for an aldehyde. You've got two options. You can either use Fehling's or Tollin's reagent. If you use Fehling's, the observation would be the solution goes from blue to a brick red precipitate. If you use Tollin's reagent, a silver mirror forms. Okay, so that's what we're looking at for that one there. Last little bit of question 7. So give a chemical reagent that would enable the student to confirm the presence of propanoic acid in the expected compounds. State what you observe when propanoic acid reacts with this reagent. So the reagent is a carbonate, but you can't just write a carbonate. You need to name a specific carbonate, okay? So we could use sodium carbonate. We could use calcium carbonate. If you wanted to be a bit random, you could use copper carbonate. It doesn't matter which one you use as long as you name a carbonate. The observation, if you add a carbonate and we've got a carboxylic acid there, you will get fizzing, but we don't write fizzing, we write effervescence, which means bubbles of carbon dioxide released. Okay? Finally, for question 7 then, predict which one of the compounds, propan-1-ol, propan-al, and propanoic acid will have the highest boiling point. Explain your answer. So let's just scribble some diagrams of these down on the left-hand side. So we've got propan-1-ol. So that means at the end, we've got the OH group. So that's on our end carbon. Propan-al means we've got a double bond OH on the end carbon. And propanoic acid, we've got a double bond O and an OH at the end of the chain. Okay, so hopefully we can spot. We need to be looking at intermolecular forces. The alcohol is going to have hydrogen bonding because of the OH group. The aldehyde is going to have dipole-dipole intermolecular forces because of the delta plus and delta minus on the carbon doubly bonded to the oxygen. But the carboxylic acid is going to have both. It's got dipole forces from the carbonyl group and it's got hydrogen bonding because of the OH group. Okay, so the highest boiling point of those two compounds is propanoic acid. That gets you your first mark. If you got that wrong, you can't get any of the remaining marks. So you have to get mark number 1 in order to get any of the explanations. So we can say it's got hydrogen bonding. Now, exam technique is important here. Whenever we discuss either hydrogen bonding, dipole-dipole, or van der Waals, you have to say between molecules or intermolecular forces. So it has hydrogen bonding between molecules or intermolecular forces. Of course, you write that out in full. If you don't put that, you don't get the mark for that bullet point. Okay? And the next mark is saying these are stronger intermolecular forces than for the remaining 2 molecules. These will be stronger than for the aldehyde or alcohol. Okay, so that's going to get you your final mark for that one. Right, last one then, moving on to question 8. So here, and this is a question which does turn into a question all about alcohols, but it picks on other bits and pieces from across the course as well. So sulfuric acid is an important chemical in many industrial and laboratory reactions. Consider the 3 reactions involving sulfuric acid. So we've got this one here with magnesium hydroxide and sulfuric acid, solid sodium bromide and sulfuric acid, and then ethene with water using concentrated sulfuric acid. Right, give a use of magnesium hydroxide in medicine. This is something which you'll have encountered in your group 2 topic. It's pure fact recollection. So you need to know magnesium hydroxide is used as an indigestion remedy or as an antacid. Okay, it neutralizes stomach acid. You could say heartburn remedy as well. Okay, sulfuric acid behaves as an oxidizing agent in reaction 2. In terms of electrons, state the meaning of the term oxidizing agent. Right, we need to remember oil, rig. Oxidation is loss of electrons, reduction is gain. Now, an oxidizing agent gets reduced. And if it gets reduced, reduction is gain. So it means it's gaining electrons. So in terms of electrons, an oxidizing agent is an electron acceptor. Okay, so that gets our mark for that one. Moving on. Give the formula of the oxidation product that is formed from sodium bromide in reaction 2. Right, this is very specific, okay? Reaction 2 refers to some very, I would say it's quite detailed chemistry of the sort of redox reactions associated with halide ions and concentrated sulfuric acid. And you just need to know that the bromide ions of sodium bromide can reduce sulfuric acid down to sulfur dioxide. That is pure fact recollection. You need to recognize as soon as we're adding a halide to sulfuric acid, we're dealing with a very specific set of redox examples that you just need to learn. Okay, so give the formula of the oxidation product formed from sodium bromide in reaction 2. So that's going to be SO2. Oh, let me just check that actually. The oxidation product, the product of the oxidation. Yes, no, that is fine. Deduce the half equation for reduction. Ah, right, no, I have done this the wrong way around. Apologies. So that's the reduction product because it's telling us sulfuric acid is reduced. So the oxidation product is the bromide ions turn into bromine. So bromine is our answer for that one. Apologies. Okay, deduce the half equation for the reduction of H2SO4 to SO2. So this, you just need to learn your rules for carrying out half equations. So H2SO4 is forming SO2. And there's a set of key rules you have to follow when balancing half equations. Rule number 1 is balance out all elements other than oxygen and hydrogen. Right, well, I've got one sulfur and we've got one sulfur, so we've done that. Rule number 2 is balance oxygen using water. Okay, so I've got 4 oxygens, I've got 2 oxygens, I need 2 more, so that means 2 waters are needed. Rule number 3 is balance hydrogens with H+. So I've got 4 hydrogens here, I've only got 2 here, so I need 2 more. And then finally, balance charge with electrons. So this side has got a 2+ charge because of the hydrogens. This side has got 0 charge. So I need 2 electrons on that left-hand side to balance that out. So that is now our balanced half equation. Okay, right, we're going to get onto the actual alcohol bit of this now. So the formation of ethanol in reaction 3 uses concentrated sulfuric acid and proceeds in 2 stages according to the following equations. So ethene with the sulfuric acid forms this, and then that intermediate, which again appears here, when we add water to it, forms our alcohol, and there's our H2SO4. So state the overall role of sulfuric acid in reaction 3. Well, if it's used in reaction 1, but it forms back again at the end of reaction 2 or stage 2, then it must be acting as a catalyst because it remains unchanged at the end. Okay, outline a mechanism for stage 1 of this reaction. Okay, so we've got a 4-mark mechanism now. So starting off with our alkene. And remember, you've got to be very specific. When we carry out this reaction with sulfuric acid, you have to represent your electrophile as H bonded to an OSO3H. So this is now linking with our alkenes topic. So because oxygen is more electronegative, that's slightly negative, leading the hydrogen to be slightly positive. Arrow number 1 from the double bond to the hydrogen, that gets you a mark. Arrow number 2 from the OH bond onto the H. These arrows have to be really specific. You can't be sloppy, they can't be about in the right place, they need to be spot on in the right place. Then that leads us to an intermediate. So let's say this is this hydrogen, which is now added onto the carbon. It means that this carbon has now got a positive charge. So we get a mark for the structure of our intermediate, our carbocation. So you need to have that plus charge on that carbon there. And then finally, we've got our OSO3H with a negative charge and lone pair on the oxygen. So that is going to attack our positive charge. That gets us our final mark. So in this situation, you don't actually get a mark for drawing out the structure of the product, mainly because they've already actually given it in the question up here. They've told us what the product is. I'm going to draw it out just for fullness anyway. So OSO3H, but that doesn't actually get a mark in this situation. Okay, moving on. State the class of alcohol to which ethanol belongs. So it is a primary alcohol. And last part, draw the displayed formula of the carboxylic acid formed when ethanol is oxidized by excess acidified potassium dichromate solution. So ethanol will go to ethanal, will go to ethanoic acid. So displayed formula. If I drew this, I would not get a mark, because a displayed formula means every single bond has to be shown, and I've cut some corners here, okay? So whenever you are asked to draw a displayed formula, it almost always involves a molecule with an OH group, because loads of people, without really thinking, just draw an OH like that, whereas actually it has to have the bond, well, it has to have the OH bond, but it has to show every single bond. So don't lose marks for sort of cutting corners and that sort of thing. Okay, right. So hopefully that's cleared up some issues. It's given you a bit of practice at some past paper questions, and you know, reinforced some of the subject knowledge from this topic already. What I'd like you to do, again, I'm not going to set it as a deadline yet, but I'd like you, when you get a chance, to keep on chipping away at your alcohols question pack and seeing how much of it you can get complete. Okay, as ever, any questions, anything you're stuck on, do get in touch with me. Do send me an email or whatever, and I'll help out as much as I can. Okay, see you soon. Thanks. Bye now.